Hi, I'm Asha Mehta.
I'm Sheikh Gussu.
I'm Jonathan Messman.
Today we're going to talk about wave particle
Duality.
Yes, sir.
So looking at the history, light was thought to either consist of waves and particles. And wave particle duality postulates that all particles exhibit both particle and wave properties. So the first to policy hypothesize about the nature of light, proposing light is a disturbance in the element of air, was Aristotle. However, Democritus, which is here, right here, who was the original atomist, argued that all things in the universe are composed of indivisible subcomponents, which are the particles. Looking back at the history, through the work of Max Planck and Albert Einstein, Niels Bohr, and many others, current scientific theory holds that all particles also have a wave nature, and vice versa. The phenomenon has been verified not only for elementary particles, but also for compound particles like atoms and molecules. So, what is wave particle duality? That is the principle of quantum physics, and holds the matter and light exhibit the behaviors of both wave and particle depending upon the circumstance of the experiment. It is a complex topic, but among the most interesting in physics. So wave particle duality in light, that's when the light is able to function as both particle and wave, depending on how the experiment is conducted and when the observations are made. Under certain conditions, such as when we shine it through narrow slits and looking at the result, which we did on our physics lab experiment, it behaves as only a wave can. And under other conditions, such as when we shine it on a metal and examine the spray of the electrons that comes off, behaves as only particles can, pretty much. This multiple personality of light is referred to as the wave-particle duality, and the light behaves as a wave or as a particle depending on what we do with it and what we try to observe out of it. So wave-particle duality in matter is just like light pretty much, and matter is also capable of exhibiting the properties of both wavelength and particles. Massive objects exhibit very small wavelengths, so small in fact that it's rather pointless to think about it in waveforms. However, in small objects that are small, the wavelength is observable, and in some cases is significant. Significance of the discovery of the wave-particle duality allowed the behavior of light and matter to be able to explain through the use of differential equation, which represents a wave function, which is the heart of quantum mechanics, which is kind of the same field. We need the concept of alternating electromagnetic field, which is the wave, to explain certain physical phenomena, like the interface pattern in two-slit experiments. So pretty much like the experiment we did in our physics lab for lab experiment number 8, I believe. So we keep that. We must somehow explain how particle orders of magnitude smaller than the distance between the slits somehow passes through the ball slit and interferes with self. However, we cannot explain this well using quanta or the particles and the photons. We have wave mechanics gives the simple, easy to understand explanation. And other part of significant of discovery is we needed the concept of quanta to explain other phenomena like the photoelectric effects, so we can keep that too, but this means that we use two different mutual exclusive system mechanics to explain the electromagnetic radiation. So one of the questions that is unanswered is the attempt to what the wave particle duality actually means is a key point to debate, in quantum physics, many interpretations exist to try to explain this, but they are all bound by the same of set of wave equation and breakthrough yet that yet hasn't occurred. Thank you.
Okay, so as my partner Mesvin said, we were investigating a duality wave particle, and we saw that actually he talks about an experiment, the interference of Young that he did, and that experience showed that actually electrons had wave property and the particle property. But everything started with Einstein. In 1905, he proposed that any electromagnetic radiation of frequency V is composed of energy packets, quantum, HV, and this is when the concept of photon was born. And the electromagnetic rays, typically undulatory, also became corpuscular, which is also synonymous for duality wave particle, meaning the same thing. And then in 1924, Broglie proposed that particles of matter, such as electrons, just as Young did, they have undulatory property, whose frequency V is given by E over H, and exactly like Einstein's photons. And this joins the duality with particle, because the matter, typically corpuscular, like electrons, also became undulatory. So we can imagine, we can ask ourselves, is Tower Cyber possible? Can we actually injure people? People can actually be injured by lasers? Yes, they can. Because as Einstein and Broglie proved it, Young too, it is actually possible to get hurt by lasers because they have this wave property, because we can see it, and they also have this particle property. And we also know that Broglie proposed this formula saying that proposed this formula relationship showing that any object having a mass actually has wave particle property, a wave and particle property. So as we can see here, the wavelength is related to the mass by this relationship lambda equals h over mv, where lambda is the wavelength, h is Planck's constant, m is the mass, and v is the frequency. So now we can imagine, can we pass through walls? No, of course not. But when you have lasers, they can pass through objects. But why is it that? If we take, for instance, a ball of mass, let's say 140 grams, then this mass becomes 0.14 kilograms. Then the velocity would be approximately, let's say, we can even say let's say 20 meters per second, which is a lot, but still, let's say 20 meters per second. And when we'll do these relations, we know that h, Planck's constant, is 6.626 times 10 to the negative 34. So in order for lambda to be considerable, we need a huge mass or a huge velocity, which is not the case for a ball. So that's why the wavelength or the undulatory property of a ball would be inconsiderable. And when we think about electrons, like in Young's interference experiment, we have lambda equals to h over the mass. The mass of electrons is really small, plus the and let's say we shot that electron at a velocity of c over 100, so we get like 2.998 times 10 to the 6th. And that's a lot times the mass, so lambda would be considerable, and that will mean that we actually have the the undulatory and the wave and the particle duality for electrons. Thank you.
So as my friend Jake showed this equation in the previous slide. So now we'll just get an example of it. And also this proves that every moving mass with a velocity has wavelength. So for example, using de Broglie, for example, we will find the wavelength of a 10 power minus 6 gram particle moving with a speed of 10 power minus 6 meter per second. And we can find it by using the Planck's constant. So the lambda is equal to the Planck's constant. This is the mass. That's minus 6 gram, which is converted into kilogram, and that's why it's 10 power minus 9 kg, and then 10 power minus 6 meters per second. That's the speed. And then after you do the calculation, you get the value of this. So that's the wavelength. Since the wavelength found in this example is so small, much smaller than any possible apertures, diffraction, or interference of such waves cannot be observed. So in short, wavelength is really small and it cannot be observed. But every mass with a moving speed has wavelength, and that's proven here. Thank you. As my friend Jay explained in his slides about the wave particle duality and how Young's experiment and how Young's interference experiment showed it, we'll get into much detail about it. And how light as a particle acts as a waves in Young's double slit experiment. Now this is Thomas Young. So the Young's double slit experiment was first conducted in 1801 by Thomas Young. It shows about the light passes through a barrier with two slits. Before it just usually used to pass through a single slit to make the light coherent. The light diffracted through each slit, created interference pattern. In order to interference the light that passes through the slit must be of the same frequency and polarization, and it must be coherent. So this is the difference between particle and waves and how lights acts as both. So in the particles, if light acts as a particle, only two slits will appear on the screen. And in the waves, the light will diffract and interfere, making many fringes. So this is a presentation of Young's double slit experiment. And this proved that light does not only act as a particle but also as a wave. So in the Thomas Young's double slit experiment, the sunlight acts as a light which passes through a screen with single slit, making a diffracted coherent spherical wavefront. These are the coherent spherical wavefront, and then it again passed through the screen with two slits, and it formed this pattern. And which crossed each other and then formed the waves. So this is how it acts. That was the experiment, and this is just a basic representation of it. Okay, so this is an example of how light acts as a waves. So I mean, you cannot see it clearly in this one, so just see it in the presentation. So the white lines, they are waves, and these are formed by many photon interference which pass through a single slit and then form the coherent spheres, and which pass through a double slit and form this type of waves. And also the time which took for this type of waves is 0.1 seconds and 3 optical depths. So yeah, that's it. Thank you so much.